Hello, and welcome to Aggressive Physics. Today is day 60, and what I'd like to do today is concentrate solely on problem solving. What we're going to do is look at a number of sample problems dealing with the force of gravity between two objects, possibly relating them to centripetal forces perhaps, and solving for some complex problems from there. These are good things that you can look back on when you're studying for a test, when you're trying to solve problems that you don't know how to solve or don't know where to start, and if you need to review for the final exam perhaps. So these sample problem days are important for us to be able to take the equations that we learned, the skills that we now have, and apply them to new situations. We'll start with some easier problems and then work our way up. Remember, you can find the force of attraction between any two objects in the universe, and those forces are going to be equal and opposite because of Newton's third law. Let's do some sample problems now. Let's get the whiteboard out and do some practice problems. Now we can actually calculate G for the sun. Now of course you're not going to be able to stand on the surface of the sun, but we can calculate it. And if you remember, force of gravity is big G, m over r squared. But if we break down Fg and make it mg, we get G m over r squared. The mass of the object involved cancels out. And to find little g, we multiply 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared times the mass of the sun, which is 2 times 10 to the 30 kilograms. And that's all over the radius of the sun. Now the radius of the sun is 6.97 times 10 to the 8 meters. And we have to square that. So 6.67 e negative 11 times 2e30 divided by 6.97 e to the 8 squared. So G for the sun is 274.6 meters per second squared. Now if you remember, we've discussed before G-force, and it's how many G's something is compared to the Earth's gravitational pull. So if you're in a roller coaster and it accelerates you at 19.6 meters per second squared, that would be considered 2 G's. Jet pilots would experience greater rates of G-force. Now in this case, if we're just comparing it to the Earth, 274.6 divided by 9.8, it's actually 28 G's. So you would be about 28 times larger in terms of your weight on the sun. Now, of course, you'd burn up and die, but you would be 28 times heavier right before you do. Pretty impressive. Sun's quite large. Let's look at another circular motion problem. And in this case, what we're going to do is we're going to take a skateboarder and we're going to put them in a full pipe. We're not even go for a half pipe this time. We're going a full pipe. And they are going to try to make a complete revolution around the full pipe. And it's a 5-meter height, which means the radius is going to be 2.5 meters. Well, how fast must they go in order to make it around without falling off and losing contact? Well, if I look at the top here, the free body diagram is going to look quite interesting. We'd have Fg and we'd have Fn, both pointing to the center, because if the wheels are pushing against the pipe at the top, the pipe is pushing down on the skateboard. Now that would mean you have the mass there, force of gravity, and the normal force. Now if we're looking at just how fast it takes to make it around, that means the normal force is approaching 0, because the wheels are still going to be gripping, but it's when they just start to let go. So that means the only force acting to the center is gravity, which is mv squared over r, because that's the centripetal force. Remember, centripetal force is always the code name, if you will, of another force. In this case, gravity's code name in this problem is centripetal force. So, if I look at the force of gravity, I don't know the mass of the skateboard, but it doesn't matter, because mg is going to equal mv squared over r. Masses cancel. G is 9.8 meters per second squared. I'm going to calculate for v, and the radius was 2.5 meters. So in order to make a full revolution without losing contact with the pipe itself, 9.8 times 2.5, second square root, second answer, you have to be going at least 4.95 meters per second. Anything less, and you'll lose contact around here and fall down. Anything greater, you're going to be safe. So this is our limiting factor. So if we're traveling at 5 meters per second, we're probably fine. If we're traveling at 4.5, we're going to fall off. So hopefully we're wearing our helmet, our elbow pads, our knee pads, and heck, we might as well be wearing full chainmail at this point. In this problem, we're going to have Coach spin a whistle in a circle around his finger. And most of the time I've seen coaches do this, they have it spin and then it gets shorter and shorter around their finger. But this coach is just going to have it spin consistently in a full circle the whole time. Now the radius of this circle is 25 centimeters. And the speed of the whistle, remember it's tangent to the circle, is 6 meters per second. And we even have the mass of the whistle, 150 grams. Well, that being said, what I want to do is find the tension at the top and the bottom of the circle. And we'll see which one is bigger. Now, at the top, as the whistle is spinning, the rope is being pulled down and gravity is downward. The mass in the box is 0.150 kilograms. If I put 150 in, that's a pretty heavy whistle. But we have 0.150 kilograms. That means the force of gravity, 0.15 times 9.8, I have 1.47 newtons. Now, both of these are contributing to the centripetal force. So, T plus Fg, they both point to the center, equals mv squared over r. T plus 1.47 equals 0.150 kilograms, 6 meters per second squared, over the radius. Now the radius is 25 centimeters, so I better put it as 0.25 meters. All right, 0.15 times 6 squared, don't need the second function, equals, divided by 0.25. I have 21.6 here, and I'm going to subtract the 1.47 minus 1.47, and I get 20.13 newtons is the tension at the top. Now let's see what happens at the bottom. At the bottom, the free body diagram is going to look a little different. The string is pulling up and gravity is still pulling down, 0.150, and the force of gravity is still 1.47. So the difference here is that the tension is inward, so that's your positive force, minus the force of gravity, which is an outward force, equals mv squared over r. Since m and v and r are the same, we're still going to get 21.6 newtons here. Force of gravity is the same, so it's 1.47 newtons. And instead of subtracting, we're going to instead add the 1.47 over. So the tension now becomes 21.6 plus 1.47, and you have 23.07 newtons. So the tension in the rope is larger at the bottom than at the top.